I'm passionate about studying solar energy. Hello, my name is Matt Sheldon. I'm an assistant professor of chemistry and materials science and engineering at Texas A&M University. My proposal is titled Rectifying Light, Nanophotonics for Thermodynamically Ideal Solar Energy Conversion. My laboratory tackles fundamental questions about nanoscience and nanotechnology, about how our ability to define matter from the atom up opens up new opportunities, in particular for applications in solar energy. Conversion efficiency is the measure of how much energy from the incident sunlight on a solar cell is converted into usable electricity. Conversion efficiency needs to be high for solar energy to be cheap. Our research is about how we can make solar cells more efficient, truly much more efficient. So the question is, how do we do this? One of the more counterintuitive aspects of a solar cell is that it is actually re-emission of radiation back towards the sun that comprises one of the main loss pathways in the most efficient devices. If we want to make a very efficient cell, what we need to do is limit this re-emission of light back towards the sun. We basically need to build something like a one-way mirror that lets light from the sun in towards the cell, but bounces back any light from the cell that might go towards the sun. Our proposal is really about how can we build a one-way mirror for photons, and this is fundamentally a very challenging problem. Our proposal is to rectify photons by building from how a conventional diode rectifies electron transport. In an electronic diode, electrons respond to two forces that affect their motion. The first is a concentration gradient. Basically, regions of high concentration of electrons will diffuse only outwards towards regions of low electron concentration. This is very analogous to how a drop of solution of concentrated dye dissolves in a solution of water. It moves from high concentration to low concentration, and it really only moves in one direction. However, unlike most dye molecules, electrons also have charge, and so as they change their concentration, that also changes the electric fields that further affects their motion. So a diode takes advantage of these two different forces acting on electrons by defining an interface, usually called a P region and an N region, that has a strong gradient in concentration across the interface. This is called the chemical potential gradient. When we operate a diode, we actually perturb this equilibrium by changing the concentration of electrons near this interface. However, because of the preferred direction for the diffusion of charges, electrons can only move one way through that interface. We take advantage of the directionality we can impose on the transfer of electrons from one state to another irreversibly, where those electronic states are also coupled to radiation with a specific frequency or direction. And by doing so, we believe we can also then constrain the flow of light energy through the system. So the meat of this proposal, how we're going to achieve this practically, is the design, synthesis, fabrication, integration, and spectroscopic characterization of materials that are designed to rectify radiation by this mechanism. So what makes this proposal unique or high risk? I'd like to emphasize the interdisciplinarity of this work. We're tackling outstanding questions in the thermodynamic theory of radiation. We're using techniques at the cutting edge of materials science and materials chemistry, and we're also using sophisticated modeling techniques from electrical engineering. For that reason, this work is not well aligned with some of the traditional strategies devised for optimizing solar cells and solar energy converters. This work is also not very well aligned with conventional strategies for rectifying photon transport, what are often called optical isolators or non-reciprocal materials. And that's because those materials are not very well applicable to solar energy. They require actual input energy, and they don't have the spectral range that makes them compatible with solar cells. Our research requires really fundamental insight into how well we can define electronic structure that's coupled to optical structure in the way that we propose is useful for this particular application. And it also requires us to overcome different types of engineering challenges. Once we make these materials, we have to figure out how to integrate them well into device-sized structures that we can actually implement in solar cells. And if we can do this well, and we can make photon rectifiers as ubiquitous as electronic rectifiers are in technology, I think we can have a lot of unanticipated breakthroughs. So thank you very much for your time and consideration of our proposal.